we have arrived at actual calculus. Section 2.2, your homework is 3 through 61 odd. Make sure that when you take these derivatives, you simplify your answer as much as possible, because pretty soon you're going to have to set that derivative equal to 0 and solve for x. Okay, so far we've learned that the derivative, written f prime of x, or dy dx, or df dx, whichever notation you prefer at this point. I'm lazy, so you'll see me write this, or even y prime. Sorry for the noise in the background. But we took that as a limit, as this is not right. Haha, I'm glad I noticed. The limit as delta x goes to 0 of the rate, the slope, right? The change in y over the change in x. This is what you practiced in the last section. You'll see that in this video for the next couple of pages, I write it with an h instead of a delta x. It's the same exact thing, just recycling a previous video for a different class, but we won't be hanging out here very long, so it doesn't matter. Remember that the derivative is the slope of the tangent line and the instantaneous rate of change. Now, if your function, f of x, is a constant, constants don't change, so your rate of change will be 0, and that makes sense. If your function is linear, in other words, x is to the first power, then you have the equation. I'm going to put a little thought bubble here. You have y equals mx plus b, right? If you have y equals mx plus b, then the slope is constant. Slope equals m, so y prime will equal m. So you should expect these outcomes. If y is a constant, then y prime, it doesn't change, right? The rate of change is 0 if you're staying the same forever. And if you are linear, it's a straight line, then your slope never changes. So your derivative will be a constant. Once you get into higher powers, you're going to get variable rates of change because you curve, right? Okay, let's do this thing. Okay, now if I have some function and I take a derivative of it, and then I take a derivative again of the same function, and I take the derivative of the same thing, am I ever going to get a different answer? Well, no. So let's look at the derivatives of the different pieces of what we might run into, say, in a polynomial, because these derivatives are not going to change. And remember, because a derivative is defined as a limit of the difference quotient, the properties of limit and the properties of derivatives are the same. So if I have a coefficient in front of an x squared, I just take the derivative of x squared and multiply the answer by the coefficient. So it's going to be important for us to know the derivatives of each of the powers of x. It's really going to pay off. And then as we get these derivatives, then we can look for patterns. Okay, so let's start with what if x is just a constant. F of x is a constant. The derivative is the limit as h goes to 0 of the ratio h in the denominator. Now, if I plug x equals x plus h into this, you see there's no x there. So the y value is always 1. The difference between f of x plus h and f of x is just 1 minus 1, which gives me 0. So when I take a derivative of a constant, let me write this down here. The derivative of a constant, prime meaning take the derivative, is just 0. Okay? Now, what if I have plain old x to the first power? The derivative is the limit as h goes to 0 of the function with x plus h in it minus the function itself over the h. Well, the top just gives me, the x's cancel, I'm left with just h. So I get h over h equals 1. What does that tell me? It tells me that the derivative of x is always 1. All right? What if I had x squared? Well, I'm going to x plus h it squared minus the function itself over h. You have to FOIL this out. We already did it. We got x squared plus 2x at hx plus h squared. Then we subtract the x squared. Those guys go away. These terms are the only ones left. I factor the h out. I cancel it. The second h goes to 0. You'll see that I'm left with that second term from when I FOILed. Same thing with x cubed. If I have x plus h and I cube it out, and off in the margin, you need to, very quickly, I'll write this down here. You need to have x plus h squared, write that answer, then you're going to get x plus h cubed by taking your previous answer and multiplying through by the x and through by the h and combine like terms. You multiplied that out, then you can multiply by another one, and you get this big cheater box here so that you can just plug and chug all of your answers in. All right, so I made a mess, and for some reason my eraser will not get big for me. All right, so when I FOIL this out, I get this right here. Notice that the x cubed and the x cubed subtract away. All of these pieces have h's. Factor it out. Once I factor it out, I can cancel it. Notice that all of these have higher powers of h. The first term, after the one you've subtracted, is the only thing that's going to not have an h, so that when I take the limit as h goes to 0, this is the only surviving bit. And my derivative of x cubed is 3x squared. Do you see any pattern? If x was to the second, I end up with a 2 multiplying, and x is to the first. If x was to the third, I end up with 3 multiplying, and my power went down. So let's examine that pattern. Now I want to show you a little something that I usually say dead Greek guy, but I think he was Italian. Pascal's triangle. I guess he couldn't get a date, so he stayed home and did math all the time, and he figured this out. So we can use this triangle. Notice that I started with the 1 at the top, and all of these are 1s down the sides of the triangle. And each of the pieces in the triangle are the sum of the 2 guys above. So I say 1 plus 1 gives me 2. 1 and 2 gives me 3. 2 and 1 gives me 3. The 3 and the 1 give me the 4. 3 and 3 is 6. 3 and 1 is 7. And you see how this triangle is built. Well, what does that represent? It's the coefficients of the binomial. Binomial meaning 2 pieces. And I'm going to raise it to the power. So if I have x plus h to the 0, that's just 1, right? If I have x plus h to the 1, that gives me 1x and 1h. If I have x plus h squared, and we did this on the previous page, we FOILed it out, we saw that we had 1x to the square in the front, h is squared in the back, and the middle was 2 times h times x. So the power of x started at the highest power here and went down until you didn't have any x's anymore. The power of h started with 0 here and went up until I had h to the power of the binomial. Let's look at the blob cubed here. These are the coefficients that you end up with. you start with x to the third and no h's. This would be 3, there's one h and two x's. Then I have 3 with h squared and x to the 1, and then I end up with 1 h's to the third, and there's no x's left. So you start with the highest power of x, and x goes down. You end with the higher power of h. You started with 0 and it went up to the highest power, and there's no x's. But the rows on the triangle represent the coefficients. Okay? Now notice that this kind of diagonal right here is the same as the power that you raised the binomial to, and that's going to come in very handy. Also notice that the first term was just plain old x to whatever power you started with. Now we said that in the difference quotient the same thing happens every time. The thing that didn't have an h in it always gets subtracted away. So that column right there is going to be subtracted off. This thing right here is, once we factor an h out, is going to be the only term that doesn't have an h left in it. All of the rest of the terms are going to have an h here and then increasing powers of h left, so that when I take my limit as h goes to 0, all of those guys are going to go away. They'll be zeros. And the only surviving bit is this guy right here, the second term. Let's demonstrate. Let's go for the derivative of x to the sixth. I know this might be hard to follow. It's so much easier when we're face to face. But let's see. You can relax for a second. Let's just plug and chug. We have once we plug this in, we've got x plus h to the sixth minus x to the sixth all over h, and then we're going to take the limit. So when we FOIL out x plus h to the sixth, we get x to the sixth, 6, x to the fifth, and an h. Then we'll get 15. The power of x goes down to 4. The power of h goes up to 2. Notice that those powers add to be 6. This is called the binomial theorem. The next coefficient is 20. The power of x went down to 3. The power of h went up to 3. Notice they add to 6. The next coefficient, looking at the triangle, is 15. 15, x went down to 2, h went up to 4. Then we have a 6. The power of x is 1. Power of h is up to 5. Then we have the last term, 1, where the power of x has gone down to nothing. The power of h has gone up to 6. And we are left with plain old h to the sixth. And now the difference quotient is going to subtract away the x to the sixth that we had at the beginning. So those guys are gone. Everybody else has an h. So we factor that h out. Notice that this is the term that has h to the first power. So when we factor out the h, he no longer has an h. It's always the second guy in the triangle. And notice that the coefficient matches the power of the thing that we're taking the derivative of. Very important. Also, we started with x to the highest power. That second term has x to the 1 power less. And we factored out the h. So this term, the second term, once we cancel the h that's on the bottom, and then we take the limit as all the rest of these guys go to 0, this is the only surviving piece. It's always the second term with the h factored out. So what happened? We end up with the power we started with as a multiplier and an exponent that has been reduced by 1. And it doesn't matter what power you started with. you now have a pattern. And this is called the power rule derivative. Anytime you take the derivative of the x to a power, you get the power is now the coefficient. So you're going to bring down the coefficient and multiply, and then you're going to subtract 1 from the power. By the way, this works no matter what the power is. Positive, negative, fraction, decimal, doesn't matter. You're going to multiply by the power and subtract 1 from the power. And it's a very simple rule. And as you start using it, it's going to become like breathing. All right? You're just going to be doing it without thinking about it. All right, let's work some example problems. So let's say we have this function 3x minus 2. The only thing, the derivative of a constant is constant. It's never changing. So his derivative would be 0. And we did that on the first page. So the derivative of 3x, notice that that's x to the first power right there, right? So when we take his derivative, we're going to have the 3 as the multiplier. We're going to multiply by the original exponent, and it's that original take away 1. You always reduce by 1. Now this gives me x to the 0, right? X to the 0 is anything to the 0 power is 1. So the only thing that survives is that 3. Notice that it was just the coefficient of x to the 1. All right, next, we're going to take the derivative of the x squared and multiply it by 4. And we're going to take the derivative of the x and multiply it by 5. And the derivative of a constant is always 0. So we have the 4. The derivative of x squared is bring the 2 down to multiply, subtract it subtract 1 from it. You know what I mean. So this gives me a 2x. 4 times 2x is 8x. All right. The second term, we're taking the derivative of x, which is 1, and multiplying it by that scalar, that coefficient, and we get 5. So you see, if we look through here, it's 2 times 4 is 8, x to the 1 plus 5. Boom, done. Do you see how that works? You don't have to write down all this busy work. You, by the end of the homework, you should be just able to write down the answers if they're just polynomials. So in this case, multiply by the 3, reduce that to 2, we get 3x squared. Multiply by the 2, that gives me negative 14, and it's x to the 1. The derivative of x is just 1, so I have plus 4. Derivative of minus 8 is 0, and there is your perfect, beautiful derivative. One more polynomial. Bring down the 4 and multiply, that gives me 12x to the 3, negative 6x to the 2, plus 5, and that's a 0. Boom. See how easy this is? So just practice the crap out of this stuff because we start learning to do products and quotients and then composite functions. You're going to need to be able to do this without thinking about it. Now, because this is so easy, the book has to make it hard, right? So here's an example of how they try to make this difficult. You don't know how to take the derivative yet of a quotient. We're going to learn it soon. But because there's a single x in the denominator, we can take that. I'm going to write this down real quick. We can take that denominator and distribute it. If it was x plus 1, we couldn't do this. But because it's plain old x, we can separate out those pieces. And you see that this guy right here is just x. This guy right here, the x's cancel. I get a minus 3. This guy, remember, division is a negative exponent. So I'm going to rewrite this guy as 4x to the minus 1 because it's first power in the denominator. Now taking the derivative of x is just 1. the derivative of minus 3 is 0. This guy is the fun part. I multiply by the minus 1 and I get negative 4. Subtract 1 from negative 1 and you're going to get negative 2. So what does that mean? Minus 4 is just minus 4. We're multiplying this by x to the negative, which means he's going to flip to the denominator and be to the positive. It's negative 4 divided by x squared. Okay, let's go over some properties of exponents really quickly. So here in my little thought bubble thingy, I've got x to the fraction. Remember, the top is the power and the bottom's the root. So I get x to the power and the root. Okay? So if I have x to the 1/2, that means it's x to the first power, second root. So I can take this guy right here and rewrite him as x to the fractional exponent. Now the derivative, power rule, derivative stays the same. I'm going to take that power and make it a multiplier. Notice that I'm doing prime now. Multiply by the power and then take the original power reduced by 1. 1/2 minus 1 gives me negative 1/2. Now, x to the minus means division. So I've got a 1 on the top, a 2 on the bottom, and the x goes to the bottom, and it's to the first power, second root. So I get 1 over 2 square roots of x. Totally cool, right? Also remember that x to the minus power means you're dividing. Anytime you have a negative exponent, you just flip it over the bar and make it to the plus. All right? If you start with a fraction, you take that power and you make it a negative on the top. So let's look at this guy right here. Ew, he's nasty. Ugh. All right. This guy right here on the bottom is x to the 1 power 3 root. But because he's on the bottom, I can bring him up to the top and make that power negative. Now, the top is just the top. The easiest way to work this problem, I know, is to take this guy and distribute him through here. Now, multiplying x times x, I'm going to have to add the powers, right? Well, that's 2, take away 1/3. 2 minus 1/3, get a common denominator. 6 minus 1 is 5/3. So that first bit is x to the 5/3. We have not started taking a derivative yet. Do not put the prime. You're just rewriting the problem as powers so that you can do the power rule derivative. Take this guy and multiply this guy. Well, that's a 1. 1 minus 1/3, common denominator. 3 minus 1 is 2/3. So this piece right here is minus 3, x to the 2/3. And then the last piece, plus 2 times x to the minus. So we've rewritten to where now we have x to the power in each of those pieces. And now we're ready to do f prime. Take the derivative. So we're going to bring the power down. 5/3 multiplies. Subtract 1 from 5/3. Over here in my little cheater box, 5/3 take away 3/3 is 2/3. So my new power is 2/3. Next problem. Multiply by the 2/3. So I get minus 3 times 2/3. Notice that the 3's cancel. I'll be left with a 2. I have to subtract 1 from that power. 2/3 take away 1 whole. I'm taking away 3/3. Leaves me with a negative 1/3. That's okay. It just means that now you're dividing by a cube root. Minus 1/3 times positive 2. Subtract 1 from the power, so minus 1/3, take away 1. Now I have minus 4/3. Bigger than 1, but we do not rewrite it as 1 1/3. We keep it as an improper fraction. Okay, what does that mean? This is a positive power, so it's multiplication. It's x to the second power, third root, and we can write it like this. Or we can write it with that guy in the numerator with the 5. Here in the second piece, the 3's canceled, so we were left with a -2. The x is to the negative, so he goes in the bottom. And the top is the power, so 1 power 3 root. This guy right here, I have a positive times a negative is a negative. I have a 2 on the top and a 3 on the bottom. And I have an x in the denominator. The top is the power, 4, and the third root. And that's my awful, ugly answer. Personally, I would have gotten a common denominator and made a whole lot more work for myself, and you would have gotten really pissed off at me for confusing you. So I decided not to do that this time. You're welcome. So you've seen throughout this video that if you have a coefficient, the coefficient just goes along for the ride and gets multiplied by the power when you bring the power down to multiply. If you have a bunch of terms added or subtracted, you see that you're just adding and subtracting the terms. You're taking this derivative term by term. The derivative is defined as a limit, and the properties of limits are the same as the properties of derivatives. A couple of last little bits to tie up here. If I have f of x is the sine of x, whatever that angle might be, we'll get into that later. Definition, the limit definition, let's see if we can work this out. Delta x goes to 0, delta x on the bottom. The sine of x plus delta x minus the sine of x. How in the world are you going to do that? Well, you're going to have to remember some of your trig identities. Let me do this in a different color here. Let's see, blue. The sine of the sum is the sine goes first, then he lets the cosine have a chance, and then we add, and the cosine goes first, and the sine goes second. And if that was subtraction, just for you to remember, then we would be subtracting those guys. So that's the sine of a sum, and the cosine of x plus y. Cosine always goes first, and she stays with her own kind. So the cosine of x, cosine of y, and then she flips the SIGN sign before she lets the SIN sign have a chance. There we go. I'm going to make a video of some basic trig stuff and post it as soon as I get a chance. Once my other classes start testing, I'll have some time to make that video and post for you. So here we have what happens when we are adding two things inside the sine function. So let's use this. Delta x goes to 0, delta x in the bottom. We have the sine of x cosine delta x plus cosine x sine delta x minus sine x all over delta x. Now this is crazy weird, isn't it? Let's see if we can do something algebraically at this point. If we stick in delta x equals 0 right now, we're just going to get 0 over 0. So here we go. I'm going to group the things that have a sine of x. That's the cosine of delta x minus 1 plus the cosine of x times the sine of delta x. Why did I do this? I don't know. Let's see. Let's split this into two fractions. So I have sine of x times cosine of delta x minus 1 over delta x plus cosine of x, watch, sine of delta x over delta x. Now we're taking the limit of each of these pieces, right? If you remember your special limits, this guy is going to go to 0, and this guy is going to go to 1. So what we have left, this guy is 0, this guy is a 1. What we have left is cosine x. All right? So what do we have? We have the derivative of the sine is the cosine. I'm going to write it sine of x prime equals cosine of x. Okay? On the next page, we'll do this, the cosine. So we have cosine of x plus delta x minus cosine of x. And we're going to do the same thing we did before using the formula, or the identity rather, for the cosine of the sum. Cosine stays with her own kind before she flips the sign, SIGN, and lets the sign have a turn, minus cosine of x. I'm going to group my cosines of x, because that's the only thing I can do. And when you're doing problems like this, you don't have to know the answer before you start working the problem, guys. I know I'm going to split this into two fractions, so I'm going to do that in this step. My second term is a minus sine of x times sine delta x over delta x. And when I take the limit of each piece, this is a special limit that goes to 0. This is a special limit that goes to 1. And I end up with f prime equals the negative sine of x. So the derivative of the cosine of x equals minus the sine of x. As we learn the derivatives of the trig functions, you'll notice, and this is just for a little mnemonic for you guys, if it starts with a c, the derivative is negative every time. And sine and cosine are each other's derivatives, except this cosine starts with a c, so you get a minus. Okay, that is it for this section. Reminding you that your homework for this section was 3 through 61 odd. Make sure you work all of these problems. Now the power rule derivative is pretty straightforward and simple, so they're going to throw junk at you, like you might have to FOIL something out. And like I said before, you're going to have to change everything to powers. If it's a root, then you have the top is the power, the bottom's the root, or you get a fractional exponent. Negative exponents are when you have x's in the denominator. The negative power means you're dividing. So get on it, y'all.